Today on the Perception in Action podcast, a look at using machine learning techniques to further our understanding of skill acquisition. How might they be used to better understand talent development, the effects of practice structure, and recovery from training? So it's time for a call to action. Hello, and thanks for joining me. This is Rob Gray from Arizona State University. I've been on a now over 25-year journey as a researcher, professor, and high-performance consultant to understand how we acquire and adapt our perceptual motor skills. Welcome to the Perception in Action podcast, where I discuss how psychological research can be applied to improving performance, accelerating skill acquisition, and designing technologies. If you're a coach or an instructor, my goal is to help you bridge the gap between research and application, and to connect your experiential knowledge with skill acquisition and motor learning theory. I want to help take you from using practice design recipes to becoming a master chef who can manipulate the key ingredients to come up with your own innovative training methods. If you're a student or fellow academic working in the skill acquisition field, I hope to keep you up to date on the latest studies and help you get to know the people working in this area. Finally, if you're developing training technologies, I hope to help you incorporate good motor learning principles in your design, pull out key performance metrics from the data, and design effective studies to evaluate your product. To learn more, help support the podcast, and or work directly with me, please check out perceptionaction.com. Now on to the show. On today's episode, I want to look at some research studies which have used machine learning to investigate skill acquisition and talent development. Very simply, machine learning algorithms are ones which build a model based on a set of variables that can then be used to make predictions without being explicitly programmed to do so. So they essentially learn what the key variables are from a set of training data that can then be used to evaluate new sets of data. They are ideal in situations when we cannot create explicit models of the underlying processes, like skill acquisition. They also have the advantage over other techniques like cluster analysis and correlation because they allow for nonlinear interactions between variables. My goal with this episode today is not to explain these techniques or the math behind them in any level of detail, but instead discuss some research studies which show their potential application in this area. The first studies I want to look at are a pair of papers published by Jones and colleagues from the University of Bangor. In setting the stage for their work, the authors emphasize what we all know to be the case. Expertise is multifaceted and multifactorial. That is, it depends on the interaction between a large number of variables. Despite this fact, we tend to isolate variables in most research studies. For example, only looking at the relationship between expertise and the volume of practice. Most sports involve physical, technical, tactical, and psychological requirements that all interact with each other. The primary goal of the first Jones et al. Paper, published in 2019, was to use machine learning to understand the factors that influence skill development in spin bowling in cricket. They note that previous studies have used machine learning methods like artificial neural networks to examine features that might predict talent ID and development. However, these tend to treat all potential variables as important, whereas in the current study, the authors use a feature selection process that reduces the inclusion of variables due to chance. The overall goal was to explore quote-unquote what makes the difference between elite and sub-elite cricket bowlers. Another important aspect of the study was that along with the quantitative machine learning component, the authors also included a qualitative analysis to understand the contributing variables in more detail. The study sample consisted of 15 elite and 13 sub-elite cricket spin bowlers. Elite bowlers had represented England on the international team at some point in their career, while the sub-elite group hadn't played any level higher than professional county cricket. Quantitative measures included various demographics, for example, birth quarter and number of siblings, a structured sporting history, which included the quantity of coach-led and unsupervised practice, competition experience, participation in other sports, etc., and major sporting milestones, including the highest level played at certain defined age periods, the age of specialization in spin bowling, etc. As I mentioned, this was a mixed method design, so qualitative data was also collected via interviews in response to questions including what was your biggest challenge along your pathway to becoming a spin bowler, and what had the single biggest influence on your development as a spin bowler. The machine learning analysis involved using these data to identify key variables which could be used to determine which group a participant belonged to, the elite or sub-elite. As I mentioned, a difference between machine learning and standard pattern recognition techniques is that it allows for non-linear interactions between the different features or variables. There were 4 different classifiers used. a support vector machine, multi-layer perceptron, naive Bayes, and a nearest neighbor. Again, see the paper if you want specific details on these. Of particular interest were features that were identified by more than one of these classifiers. As is often done with this type of analysis, after the classification, algorithms were allowed to learn to discriminate between sub-elite and elite bowlers on the training data set. They were then tested on another set of data they had not seen before. For this, 5 additional spin bowlers, 3 elite and 2 sub-elite, were interviewed. What was found? From the total of 96 features in the data collection, the machine learning algorithm identified 12 that could be used to classify bowlers into elite or sub-elite groups. These were the highest level of cricket representation by age 14, age first joined a county cricket academy, years taken to become the best spin bowler in county cricket, proportion of competition overs bowled up to county debut, age decision made to become a professional cricketer, years taken to achieve a significant performance in senior club cricket, cricket competition hours up to senior international debut, age of first involvement in unsupervised cricket practice, and age of first regular involvement in cricket, birth quarter, and proportion of spin bowling specific practice up to the age of 14. All of these features appeared in at least 2 of the 4 feature selection methods used. These 12 features can be grouped into 4 major themes: early development, pathway milestones, domain-specific activity, and pathway performance indicators. Overall, the support vector machine had the greatest classification accuracy with a value of 93%. Finally, in terms of classifying bowlers for the new untrained dataset, this 12-feature model classified all of these bowlers correctly. In terms of the qualitative content analysis, the interviews identified themes that fit very well with the feature classification. Specifically, bowlers indicated that the biggest developmental challenge was getting selected for the team and avoiding being deselected. The spin bowlers successfully overcame challenges by seeking advice and feedback from experienced bowlers and coaches, and they reported that significant others had a big influence on their development. As summed up by the authors, quote, "The study serves to highlight the importance of adopting a holistic approach in expertise research to enable the examination of the multifaceted and complex nature of expertise development. And the study offers sophisticated analysis methods to achieve this, thus producing a series of applied recommendations in collaboration with the England Cricket Board. We suggest that priorities in England and Wales cricket now lie in profiling youth spin bowlers against the model to identify potential areas for development. To that end, it's equally important to address current development processes in academies that appear to hamper or discourage development areas across the 12 features highlighted." End quote. Earlier this year, Jones and colleagues conducted a follow-up study to examine how the structure of practice influenced and interacted with the developmental characteristics in cricket. In particular, they sought to evaluate the effects of variability of practice and contextual interference. For this study, 20 cricket batsmen, 10 super elite who represented their country internationally, and 10 elite who played a minimum of 100 innings professionally at the first-class county level were interviewed. Along with the questions about demographics, milestones, and performance indicators, the interview included a section related to the nature of and microstructure of practice. Specifically, players were asked to what extent they participated in deliberate play, deliberate cricket activity, mental skills training, how practice was structured, for example, the speed and types of bowlers they faced, the level of difficulty of practice, and the types of feedback they received. For the analysis, a matched pair design was used. For this, each super elite batter was paired with an elite batter that shared similar demographics, for example, batting position, educational background, etc. As the authors state, quote, "Matching participants on the identified key characteristics assisted in exploring why batsmen digress in their eventual expertise despite their common characteristics, thus enabling the present study to address the question of what makes the difference." Machine learning algorithms were again trained to classify batters into the super elite and elite groups, and then tested on a set of players that were not in this training data set. What was found? 18 features were put into a combined final classification model with an overall accuracy of 96%. The model again classified the non-tested data with 100% accuracy. Some of the features that were used to classify batters were as follows. As compared to elite players, super elites have more siblings who are older, engaged in a larger volume of cricket practice activity at age 16, practiced a greater number of shots during their random batting practice at age 16, and undertook a larger volume of random variable batting practice with maximum variation at age 16. More specifically, to quote the authors, examination of the microstructure of practice at age 16 revealed that the super elite players had also undertaken a larger volume of random practice with greater variability, discriminating them from the elite. Specifically, the super elite batsmen reported undertaking a larger volume of practice indicative of scoring-based scenarios, which challenge players to develop and execute run scoring based on game information. In addition, the super elite's random practice was also more random in nature at age 16, as they practiced a greater number of shots. Interestingly, the types of bowling deliveries faced, for example, fast versus swing bowling, did not discriminate between the two groups. Finally, quote, overall, the findings demonstrate that random practice and variability in practice relatively early in a batsman's development, at age 16, are precursors of super elite expertise. Although highly random and varied practice is often considered detrimental to performance during early skill acquisition due to the increased challenge associated with its dynamic nature, the present finding reaffirms previous evidence of its long-term benefits. End quote. The next study I want to look at today is one published this year by Diu and colleagues. In it, the authors used a machine learning approach to identify the relationship between skill level in badminton and movement on the court during gameplay. 40 French players were first classified into one of 5 skill levels using something called a conative stage analysis. This involved videotaping them during play and then having expert coaches classify them into a stage. The stages were as follows. 1. Structural, defined as a player seeing the shuttle as an obstacle and just wanting to get it back over the net with each shot. 2. Functional, defined as trying to place the shuttle in space to make their opponent move around. 3. Technical, defined as the player always trying to position themselves in a good position to play a smash shot. 4. Contextual, defined as the player having a strategy where they combine shots into space and smashes. And finally, 5. Expert, defined as having a strategy that can also be adapted to the specific abilities of their opponent. Players next played a set of badminton while wearing an accelerometer attached to their belt. This tracked movements up, down, left, right, forward, back, etc. The authors used this data to calculate a variety of different variables, including the amount of total exertion along a given dimension, the ratio of movement laterally and forward, etc. The machine learning algorithm was trained to learn to classify players into one of the 5 conation stages by identifying features from the accelerometer data and also from the duration of the rallies. What was found? The best classifier had 58% accuracy. The classification features identified by the machine learning algorithm were the duration of rallies, the ratio of movement between and during rallies, and the amount of forward and back movement. So, overall, I think this is an interesting attempt to link subjective assessments of performance with quantitative movement data. Finally today, in a study published in 2011, Mezek and Arnold used a machine learning approach to determine the variables which influence recovery from training and swimming. Data collected included information about age, sleep, measures of heart rate and pulse, amount and type of land and water training. These were used to classify swimmers into groups based on their subjective assessment of how they felt during practice the next day. A fuzzy logic machine learning approach was used to identify ranges in these variables. So for example, if the amount of sleep fell between 6 and 8 hours, the participant would fall into the 5 out of 5 feeling group. What was found? The final model classified the swimmers with an accuracy of 68%. The features that were identified to be associated with the highest positive ratings of feelings at the next day's practice were as follows. In the previous day, the swimmers went to sleep between 10 p.m. and 2 a.m. The difference between pulse before going to sleep in the day preceding the training and the pulse after waking up was in the range of 1.5 to 2.9. The duration of training during the day preceding was no longer than 45 minutes. The number of kilometers swum in the previous training day was less than 11.5. So although the measurement of recovery was a bit crude here, I think the study does show the potential of using a machine learning approach to understand how activities during and after practice influence recovery. So, to sum up, I think machine learning offers a lot of promise for the field of skill acquisition. It addresses 2 of the main challenges we face now. First, we know that how people learn and improve motor skills is a highly multifactorial interactive process. Thus, it's unlikely that we're going to be able to identify simple laws or rules for success. Allowing these classifier algorithms to pull out key features is a great way to find the needles in the haystack and identify and test things that we think are most critical. Second, in almost every sport now, we have so much data lying around that in many cases we're doing nothing with it. Machine learning offers a way to pull something out of it, even when we don't really have any clear predictions or ideas of what we're looking for beforehand. Okay, that's it for today's episode. Remember, you can contact me at robgray@asu.edu or follow me on Twitter at ShakyWeights. To find out more about the podcast, please check out perceptionaction.com. Finally, to support the podcast and receive bonus materials, including written transcripts, please head over to patreon.com/perceptionaction. This is Rob Gray from ASU. Cheers for now, and keep 'em coupled. Straight away.